Okay everyone, let's go ahead and take a look at how integrals, particular integral, is going to produce the inverse trig functions. Now remember, when we actually did the differentiation of the inverse trig functions, we came up with a function that was a rational radical function. So just by inspection here, I'm hoping that everybody will take a look at this and say, hey, that kind of looks very similar to what the inverse sine function looks like. And sure enough it is, but the one thing that we need to be careful is that we keep this constant open in the sense that it could be any constant that we want, and so we'll go ahead and call it a squared. So what we're going to do is we're going to go ahead and use what is called a trig substitution in order to go ahead and derive the integral which produces the inverse trig function. So let's go ahead and say that x is going to be equal to a sine theta. Now why am I choosing this particular substitution here? It's because what we want to try to do is we want to try to eliminate this radical. Now watch what happens. If I go ahead and take the derivative of both sides with respect to theta, I come out with d of x is equal to a cosine theta d of theta. So what happens then is that the d of x is going to be substituted with a cosine theta d of theta, and the denominator is going to be the square root of a squared minus a squared sine squared theta. Now, what we can do here is we're going to go ahead and take a look at this on the side, is that I can go ahead and factor out a squared, and then the square root of a squared is just going to be a, so that's the factor there. And then I have the square root of 1 minus sine squared. Well, we know that the square root of 1 minus sine squared is the same thing as the square root of cosine squared theta, and that's just going to be cosine theta. So notice that what happens then is that this denominator part here, which is a radical, becomes simply a cosine theta. And notice that in the numerator I also have a cosine theta d of theta. So what I have then is I have a cancellation there, and it just come out with the integral of d of theta. So what is that? That's just going to be theta plus c. Now remember, the original question that we dealt with was in terms of x and this parameter a. So what I need to do then is I need to go ahead and change theta in terms of x and a. Well, I know that x was equal to a sine theta, so that means that sine theta is equal to x over a. That means that theta is going to be equal to the inverse sine of x over a. So what I have then is inverse sine of x over a plus c. So if I start off with something that looks like this, by using a trig substitution, I can go ahead and integrate and come up with one of my inverse trig functions. Now the other one that we should be familiar with as well is something that looks like 1 over a squared plus x squared d of x. And I'm hoping again that everybody will think, hey, that's kind of very similar to the inverse tangent. And sure enough, if we go ahead and do another trig substitution, what we'll see is that you will in fact come up with the inverse tangent. So if we go ahead and say that x is going to be equal to a tangent theta, again using a trig substitution, then d of x is going to be equal to a secant squared theta d of theta. So if I go ahead and take the rewrite this integral in terms of a and theta, I have a secant squared theta d of theta divided by a squared plus a squared tan squared theta. If I factor out the a squared, then I got 1 plus tan squared theta. That's the same thing as the secant squared theta. So notice what happens is that the secant squared thetas will cancel, and I'm left with the integral of d of theta over a. So 1 over a is just going to be a scalar multiple, so I can just put that on in the front, and the integral of d of theta is just going to be theta, and then add the constant of integration. So I go through the same process again, and I say, well, I know that x is going to be equal to a tangent theta, so if I want to find out what theta is, I divide both sides by a, and then take the inverse tangent to come up with this particular inverse trig function. So if we start off with something that looks like this, I can again use a trigonometric substitution to simplify this integral to something that looks like the inverse tangent function. So if you want to go ahead and memorize these, that's of course fine. If you forget them, you still know how to go about deriving them as well. So just to wrap up, if we go ahead and notice that we have something that looks like this, or something that looks like that, which is very similar to the derivatives of our inverse trig functions, then we want to go ahead and use a trigonometric substitution to go ahead and come out with our inverse trig function as the integral itself. Okay, so let's go ahead and see if we can do some of these problems. We'll work through some of them in class, and let's see how we do. Okay, see you later. Bye-bye.